Okay, any questions before we continue? Okay, so we had this example. We had this wheel. Now you can also think of a sphere. The idea will mainly be the same. You have an axis passing through this point. And you have an axis passing through this point. So they are perpendicular to each other. Both of them are in the plane of the wheel. But we know that if you rotate the wheel by 90 degrees, the wheel doesn't change. Nothing changes. So that basically means that these two moments of inertia should be equal. So if I calculate the moment of inertia passing through this axis or moment of inertia passing through this axis, they should be the same. Now we can use the perpendicular axis theorem, which told us that I have this point. So I have these two axes passing through this point and at the same time in the plane of my thin object. In that case, the moment of inertia for the perpendicular object, which is nothing but this one, well, this I center of mass is the moment of inertia for rotations passing through rotations around an axis passing through this point perpendicular to the plane of my wheel. So I center of mass is equal to I center of mass prime plus I center of mass double prime. So these two are the moments of inertia for rotations around two axes that are perpendicular to each other and in the plane of my object. And this is the perpendicular axis. But we know that these two are the same. So which tells me that I center of mass prime, which is equal to I center of mass double prime, should be equal to I center of mass over 2, which will be m times r squared over 2. Now we can even calculate the moment of inertia for an axis passing through here. Let's call that I tilde. So I have my wheel. First, we calculated the moment of inertia for rotations around this axis. From this one, we obtained the moment of inertia for rotations around this axis. And we also calculated the moment of inertia for this axis, which is the same as this axis. Just this is a wheel. And now, since we know the moment of inertia for rotations around this axis, we can also calculate the moment of inertia for rotations around this one. If you want to rotate your wheel like this is what you will need. And to do that, we can just use the parallel axis because I already know the moment of inertia for this axis. I have to move this axis parallelly to this point. But I already know how much the moment of inertia changes if I just shift my axis from an axis passing through the center of mass. This still passes through the center of mass, both of this axis and this axis, they pass through the center of mass. So I can just shift them to this point if I just shift it by a distance r. So that moment of inertia, I tilde, will be equal to I center of mass prime plus mr squared, which is 3 over 2 m times r squared. So if I know one moment of inertia, these two theorems just allow me to obtain others. Well, still I cannot obtain using these theorems the moment of inertia of, let's say, for rotations around an axis passing around this axis. I still cannot obtain that. But nevertheless, it just reduced some of my work. Now, any questions up to here? Now, these things will become more clear once you do some exercises on them. Now, what I would like to do is I would like to study the kinetic energy of an object which is translating and rotating. So just imagine that you have this ball. Let's say you just give it a spin and you let it move. How can I write its kinetic energy? So I have this object which is moving. Now, nowadays, the translational motion, from now on, whenever we are talking about the translational motion, we will be mainly dealing with center of mass. The center of mass is moving. But at the same time, we said that we can describe it as rotating around this point, let's say. Let's just take that point to start with. So this object is rotating, and at the same time, it is moving in some direction. How can I write the kinetic energy? Now, we had already said that this rotational motion, to describe this rotational motion, I can choose any axis. Let's say this is the center of mass. We will eventually go to the center of mass. But to start with, let's just choose this point. It is rotating around this point. Well, if I want to calculate the kinetic energy, first I have to choose some coordinate axis, some reference frame. This is my inertial reference frame. I'm just looking at the ball, let's say. I chose an axis. This one, it is rotating around this axis, this point, an axis passing through this point. Now, the kinetic energy of my object is nothing but the sum of the kinetic energies of the point objects making my system. So I just imagine that I divide this ball into very small bits. Each bit has a mass mi, and they have a speed vi relative to this inertial reference frame. Now, I want to separate two motions. What I want to do is I want to separate the motion of the center of mass and the motion of each one of these points relative to the center of mass. So because the motion relative, no, not the center of mass, the motion of this axis and the motion of the object relative to that axis, because the motion relative to that axis, I said that it is the rotational motion. We already studied the rotational motion. So I want to separate the rotational motion from the translational motion of the axis. And let's see what will it look like. Now we can just take some point, some small mass. And that small mass, let's say its position, vector relative to my inertial reference frame is Ri. So and its position relative to this rotation axis is just di. So this Ri, no, sorry. Let me change my notation a bit. This is large R, capital R. This is the position of the axis of rotation. Ri is the position of that very small mass that I'm studying. And again, this is di. So this R is the position vector of the rotation axis. For the time being, it's not necessarily the center of mass. Small Ri is the position of the mass mi relative to the inertial reference frame. And di is the position of the mass mi relative to rotation axis. Of course, I chose a specific point on the rotation axis, and this large R would be the position of that reference point on the axis. di is the position of mi relative to that reference point. And then we know that, if you just remember vector addition tells me that this small ri vector is nothing but the large R plus di. Any questions up to this point? This is the position of the axis. This is the position of my mass relative to the axis. So if I just sum them up, I get the position relative to my inertial reference frame. But this also tells me that the velocity vi is equal to large V, which is the velocity of the center of the rotation axis, plus, let's call it ui. Ui is the velocity relative to the axis. Now we can write down the kinetic energy. Now the total kinetic energy will be 1 over 2 mi vi squared. I'm just summing over all the particles. This is equal to sum over 1 over 2 mi vi squared. Now v squared plus 1 over 2 mi ui squared plus 1 over 2 mi times twice v dot ui. What I did is I just took this expression, put it over here, take its square. Now let's look at the first term. Now this v, this large v, it is the velocity of the axis of rotation. It doesn't change. You hear all the sound of the changes, but this doesn't change from one mass to the other one. So I can just take it out of the sum, and what I am left with, this is equal to 1 over 2 m v squared. So this is kind of nice, because if the object is moving with some velocity v, I would expect to have some kinetic energy of this form. Plus, if it is rotating around that axis, I would expect the kinetic energy of rotation. It will be this one. Because you see, here this ui is the velocity relative to the rotation axis. So we can just imagine that we go to a reference frame in which the rotation axis is fixed. In that reference frame, this ui, that would be an non-inertial reference frame most of the time, by the way. But in that reference frame, this ui will be the velocity of that point. But the velocity of that point is nothing but the angular velocity times the distance from the origin. So ui is in fact omega times, let me use some different symbol. No, that's correct. Omega times di. This di being the distance from the rotation axis. So plus 1 over 2 omega squared mi di squared. Well, this is also nice. This is, okay, it is rotating around an axis with angular velocity omega. This is 1 over 2. Does this ring any bells? Yes. This is the moment of inertia for rotations around the axis that we had chosen. This is I. So this is the kinetic energy due to the translational motion of my axis. This is the kinetic energy due to the rotation around that axis. I have one more term. Plus v dot mi ui. Okay, does this ring any bells?
Position of center of mass.
It's not the position of the center of mass, it's an average of the velocities. Well, it's not necessarily 0. Well, these two terms is what we would have naively guessed. We would have said, okay, if it is a translation of the axis plus it is rotating around the axis, then there is the kinetic energy for the translation of the axis plus the kinetic energy corresponding to rotations around the axis. Then we have this additional term in the kinetic energy. But we can still get rid of this term if we choose the axis to be passing through the center of mass. So this is our kinetic energy. There is nothing much we can do about this. This MI/UI would be nothing but the velocity of the center of mass. So you see the kinetic energy is now 1 over 2 mv squared plus 1 over 2 I omega squared plus m times v times u center of mass. This u center of mass is the velocity of the center of mass relative to the axis. Well, you see, mi, mass times the velocity, is nothing but the momentum. So this is the total momentum. And if you remember, we always wrote the total momentum of an object as the total mass times the velocity of the center of mass. But of course, here the velocities are all relative to the rotation axis. So the velocity we have over here should also, the velocity of the center of mass is also relative to the rotation axis. This is the velocity of the center of mass relative to the rotation axis. So in the kinetic energy expression, okay, these two are nice. This is something that we didn't expect, but it's just there. But we can get rid of it. Now, we can get rid of it if we choose the rotation axis to pass through the center of mass. If we choose the rotation, up to now we said that you can choose whichever axis you like. There is no criteria. Everything will give you a justified answer, a correct answer if you do everything properly. Properly, for example, the kinetic energy, if you want to write the kinetic energy of the object, this is the correct expression. This is the full expression. You have the kinetic energy of translation of the rotation axis, the kinetic energy for rotations around the kinetic axis, or around the rotation axis, plus this additional term. If you keep all of these things, you can just choose whichever rotation axis you want. But if you want to simplify your calculation by getting rid of this term, you have to choose an axis, a rotation axis, that passes through the center of mass. In such a case, the velocity of the center of mass relative to an axis passing through the center of mass will be 0, because the axis is also moving with the center of mass. So the center of mass is always on your axis, always at the same point, so its velocity of the center of mass relative to your point will also be 0. So this is 0, and hence the kinetic energy you can always write as 1 over 2 mv center of mass squared plus 1 over 2 I center of mass times omega squared. Now again, if you look at this separation, this is the kinetic energy of the object as a whole. This is something that you can call the internal energy. This is another form of the internal energy. If your object is rotating, you can say that this is the internal energy of the system. It is not due to the overall motion of the system, but due to just rotations inside.
What's the difference when we choose the rotation axis as center of mass or another point? Because there's no difference.
You can choose whichever one you like. You can choose whichever axis. The only criteria is that its direction is fixed. You cannot change its direction. At least in the systems that we will be studying, the direction will be always fixed. You can choose whichever one you like. But if you want to write the total kinetic energy of your system, this is the full expression for an arbitrary rotation axis. For the special case of if you choose a rotation axis that passes through the center of mass, well, since you are free to choose any axis, you can also choose an axis that passes through the center of mass, then the kinetic energy just splits into two parts. One, the total translational energy of the center of mass, plus the rotations around the center of mass. That's something special about the axis passing through the center of mass. It simplifies your calculations. But if you want to choose some other axis, fine, choose another axis. Sure. No, I mean, if you choose some other axis and use the v of that some other axis and the moment of inertia of some other axis, this expression and this one and that other axis are not the same. If you calculate this one for any axis and compare it with this expression for the center of mass, you will see that these two are always the same. Because you see, our starting point, our definition of the kinetic energy, this one. In that expression, we didn't choose any rotation axis anyway. We just chose some inertial reference frame, and in this inertial reference frame, all these points have they all have their velocities. But what we did was we said that, okay, let's divide those velocities into two parts. The velocity of the rotation axis plus velocity due to the rotations around that axis. So we just wanted to make such a separation. And what we had seen at the end is that we cannot really separate these two for an arbitrary rotation axis. This is the expression we have. This is these two terms, they are well separated, but if you see here, this is this is due to rotations, but this is due to the translation of the center of mass, or translation of the axis. We couldn't separate these two motions, the rotation around the center of mass and around the rotation axis and the translation of the rotation axis. We couldn't separate them for an arbitrary axis. But for one particular axis, the one that goes through the center of mass, we have this full separation between these two motions. The translational motion of this axis passing through the center of mass and the rotation around that axis. But in any case, whichever axis you choose, we are always calculating this quantity which doesn't know about any axis. Other questions? Now let's see if the parallel axis theorem makes sense from this result. Remember, we had this rolling motion. We had this object that was rolling down. Let's imagine that we look at it at one moment. And then we want to calculate its kinetic energy at that moment. And at that moment, let's assume that it is rotating with an angular velocity omega. It doesn't even need to be a ring. Just an arbitrary shaped object rolling down without slipping. So we said that at this instant, this point is at rest. So what is the kinetic energy? Kinetic energy of my object as a whole. Remember, for a fixed axis, if the axis is fixed, now we already used the fact that for rotations around the fixed axis, the kinetic energy is 1/2I omega squared. Well, it is also, you can also see it over here. If our rotation axis is fixed, this term is 0, this term is 0, the kinetic energy is always 1/2I omega squared. Kinetic energy is 1/2I omega squared. Of course, this moment of inertia is the moment of inertia for rotations around the point A, around this point. not for rotations around an axis passing through the center of mass. Okay, this is one expression of the kinetic energy. Now we can also write this as the kinetic energy as 1 over 2 m, the velocity of the center of mass squared plus 1 over 2 I center of mass times omega squared. And we just said that these two kinetic energies, they should be the same, this term and this term. Now we also know that the velocity of the center of mass, you see it is at a distance r from my rotation axis, so it's moving, the speed of the center of mass is nothing but r times omega. Now if you look at, if we just substitute it over in the above expression, this is equal to 1 over 2 m omega r squared plus 1 over 2 I center of mass times omega squared. This is equal to 1 over 2 I center of mass plus mr squared times omega squared. And this has to be equal to 1 over 2 moment of inertia for rotations around A times omega squared. But this is also what the parallel axis theorem tells me. The moment of inertia for rotations around A is equal to I center of mass plus m times r squared. If the parallel axis, or you can just interpret it in another way, you can say that if the parallel axis theorem is correct, if this is satisfied, then this kinetic energy written in terms of the velocity of the center of mass and rotations around an axis passing through the center of mass is equal to the kinetic energy obtained as writing the kinetic energy as the rotations around this fixed axis, around an axis passing through this fixed point. So if the parallel axis theorem holds, then these two kinetic energies, they are equal. Well, the kinetic energies have to be equal, so the parallel axis theorem have to be correct. No, in this one we are not following its motion. We are just saying that it is rolling down without slipping. I don't know what the acceleration is, etc. I don't know how long it has been rolling. But at a given instant, I'm looking at the object. It is rotating with angular velocity omega, and I'm calculating its kinetic energy at that instant. There might be friction, there might be other effects whatsoever. I don't really consider them. The only thing I know is that it is rolling without slipping down an incline, and at a given instant, it has angular velocity omega. No. It can be going upward, it can be going downward. In any case,
it doesn't matter.
It doesn't matter. Because I'm looking at an instant. If I want to see whether it is going upward or downward, I have to look at what happens at the next instant. Or if I have to calculate its acceleration, etc., whether the acceleration, I have to determine which direction the acceleration is.
This is also important, acceleration. Because we are looking at moment.
Well, if we want to study the acceleration, that means we are looking at one moment and the next one.
The same equations changing the orientation.
The inclination of the plane.
Yes.
I mean, you see here, I never use the inclination of the plane. If I change the inclination of the plane, the only thing that will be modified is its acceleration. But I don't care about the acceleration. The only, at least in this treatment, in this discussion, the only thing I care about is that it is rolling without slipping, so that this point is an instantaneously fixed axis of rotation.
But isn't the acceleration causes the rolling?
Sure. No, I mean, acceleration will determine what the angular velocity is. So if you want to calculate what the angular velocity is at a given time, then of course you have to calculate the angular acceleration, you have to take into account this inclination of the plane, etc. But we are already given that at the instant we are looking, this is the angular velocity. The change in the inclination will affect how long it took for the object to come to this angular velocity, for example. But I'm not interested in that one. I'm just interested in calculating the kinetic energy at this instant, when I'm already told that this is the angular velocity. Of course, the inclination will affect how the angular velocity changes, or how the kinetic energy will change as a function of time. If you change the inclination, the change in the rate of change of the kinetic energy will be different. But I'm not looking at how the kinetic energy changes, neither how the angular velocity changes. In this one, I'm only comparing the expressions for the kinetic energy using two different descriptions of the motion. In one description, I'm saying that at this instant, it is rotating around this fixed axis. That is one description of the motion. Another description of the same motion is that the object is rotating around an axis passing through the center of mass, and the center of mass is moving with some velocity, the center of mass. These two descriptions, they are different descriptions of the same motion, but they are both true, and what this shows is that they are consistent with each other. They give me the same kinetic energy, for example, because the kinetic energy is independent of which axis I choose to describe my rotation. That is the point of this exercise. Other questions?
If the kinetic energy doesn't change the axis, then we try to apply a force to an object. It matters where you apply it.
Okay.
But you say that the kinetic energy doesn't change. Uyguladığımız yere göre değişmiyor.
No, that's not what I'm saying. Now, what I'm saying here is that all those effects, like the inclination, or if there are any other forces, I didn't even tell you that this is a free object. You might be just pushing it with your hand uphill or downhill. All of these forces will change how angular velocity will change as a function of time. What I'm saying is that the kinetic energy depends only on angular velocity. And of course the velocity of the center of mass, which is again depends on the angular velocity. Once you tell me what angular velocity is, then I can calculate the kinetic energy without any knowledge about any other facts, like the inclination, like any other force there is. Of course, those forces will affect how angular velocity changes, or what the exact value of angular velocity is. But once I am given that, once I am told what the angular velocity is, then I can calculate the kinetic energy without knowing this inclination or any other forces that causes the object to have this angular velocity. If there are other forces, etc., in that case, of course, they will change the angular velocity. They will affect how the angular velocity changes, and hence how the kinetic energy changes. They will only influence the changes in the kinetic energy.
Because the expression, we think that the object is rotating around the A point.
Yes?
If there's a B point on the top of the object,
Okay.
and we describe according to this point.
Okay. Well, so you want to calculate the kinetic energy relative to the point B. Let's give it a try. Kinetic energy relative to the point B. Now it will be 1 over 2 mvb squared plus 1 over 2 ib times omega squared. Okay, two things to note. One, okay, the moment of inertia depends on which axis you choose. So since I'm now choosing an axis B, I'm choosing the axis B, so the moment of inertia is different. But angular velocity is independent of the axis. If you change your axis, angular velocity will still be the same. So it's still B over omega over here, it's not omega B. Then, of course, I have to add one more term. I have to add mvb dot u, center of mass. Now, IB, again, I can use the parallel axis theorem, which is I center of mass plus mr squared. Well, the I center of mass is also mr squared, so this is twice mr squared. This is IB. Well, in fact, this is also IA, because A and the B points are at the same distance from the center. VB, now let's choose this axis to be our x. No. X-axis is down the incline. So my point B is moving down the incline with velocity 2v center of mass.
Point A is 0.
Point A is 0. Point B will be twice the velocity of the center of mass relative to our inertial reference frame, by the way. So this will be equal to twice omega r in the x direction. U center of mass, this is the velocity of the center of mass relative to our rotation axis. So you see this is moving in this direction with 2v center of mass. So the velocity of the center of mass relative to that point, our rotation axis, is minus v center of mass, minus omega r in the x-hat direction. So let's write down the kinetic energy. Kinetic energy of the object calculated relative to describing the motion as if it is rotating around the axis passing through B. This is equal to 1 over 2 m, okay, Vb squared is 4 omega r squared, plus 1 over 2 Ib is twice m omega r squared, minus m times the scalar product of these two vectors, which will be minus 2 omega r, well, minus 2 omega r squared. If we just sum them all up, they're all m omega r squared. I have 2 over here, 1 more from here, 3. So this should be plus. So I have 2 plus 1, 3, minus 2, 1, m times omega r squared, or 1 over 2 times 2m r squared times omega squared. This is IA. So still, whatever axis you choose, the total kinetic energy of the system is always the same.
That should be omega squared.
True. This is also omega squared r squared. So if you choose a different axis, not B but some other axis, still this will hold. This expression for the kinetic energy is always the same, and it will be independent of which axis you choose. Any other questions? So I have this rigid body. These dashed lines show me circles. These dashed lines are circles. The inner one has radius RA, the middle one RB, and the outermost one has radius RC. Then I have these points A, B, and C. For those points, I can talk about their angular velocities and also their linear velocities. I just want you to order the angular velocities of these points and the linear velocities of these points from smaller to the larger or larger to the smaller. No, you don't need to write any explanations. Just write the answer, that's enough. This is the axis of rotation. Well, the axis of rotation passes through that point, let's say. It's perpendicular. Let me also show the direction of the angular velocity. Oh, no, okay. This is the rotation axis. Don't forget to give one full page. Don't tear your pages into two. When you are done, you can just give your quiz and leave silently. You can start chatting when you're out. And everybody should bring their own quizzes. You should chat when you go out.